So good afternoon or good morning, depending on where you're joining us from, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those who don't know, we are all about bringing conservation, adventure, and science into classrooms around the world. And all November long, we have been featuring amazing storytellers and speakers, astronauts, and more that work in space and out in space. So it's been a lot of fun, and we appreciate you guys joining us for the month. Right now, we've got 7 classes from across North America with us, so I'm going to give them a chance to do a bit of a shout out. We've got Miss Searson's grade 3, Douglas, Ontario. Hey guys, oh, they're coming in, guys. Oh, they're coming in.
Yeah, they're coming in.
Perfect. We've got Miss Carton's grade 6s in Anchorage, Alaska.
That was the introduction.
Hey, we've got Miss Russell's grade 8s in Brampton, Ontario. Setting the bar very high for excitement. We've got Miss King's grade 9s in Calgary, Alberta. It's like one kid was super high pitched there. We've got Mrs. Caracassis in grade 7s in Brampton, Ontario. Coming in. We've got Miss Goff's grade 3s in San Antonio, Texas. To break the mic, and we've got Mr. Windish's grade 4s in Coeur d'Alene, Idaho.
Wow.
That's just like that was a very enthusiastic. Okay.
Yeah.
Of course, the reason you guys are all here today is for our speaker. So we are joined live from a conference room at NASA's Jet Propulsion Laboratory in California, one of the most storied and iconic research facilities in the entire world, by Bobak Ferdowsi. So Ferdowsi with a soft W, like he said. And he is a spacecraft systems engineer who has worked on projects from Curiosity, currently on Mars, to Cassini, going out to Saturn, and is currently the Fault Protection Lead on NISAR, which is a joint Earth observation mission with India. So he works on robots to go to other planets across our solar system and look back at Earth to find out more about life here. So it's a very cool job, probably the coolest job in the entire world. Without further ado, I'll turn it over to you.
Awesome.
Okay.
Hello, everybody. So I'm going to switch to PowerPoint real fast so you guys can see some sweet pictures of space. Otherwise, you'll be looking at my face the whole time, which is not as exciting. So let me do that. And say that. And of course, it's not showing up here on my screen. Yep. Let me pull it onto the same.
You can sit on the top.
Let's see if this helps. Screen share.
Do you want to sit on a chair?
All right. Yep, there it is.
There you go.
There we go. All right, guys. So yeah, one of the things I work on is looking for life with robots. Obviously, a lot of life here on Earth, but we're trying to find life elsewhere. And if you think about it, there's a couple of reasons for that. One, we just want to understand if we're alone in the universe, and two, we just kind of want to understand what life is supposed to look like. For everything that looks on Earth, we've essentially come from the same branches of an evolutionary tree. But we don't know if everywhere in the universe that's a universal constant, whether that's true or not, or whether maybe life can arise in different ways. So one of the things we do is to look at our neighboring planets and moons and places like that as ways of trying to figure that out and maybe what could happen there. So we're going to go through a quick tour of the solar system real fast here. Oh, first I'm going to give you an introduction. Hello. I'm Bobak, and I work at NASA's Jet Propulsion Laboratory. We do robotic spacecraft. So for those of you guys who are familiar with NASA in general, there's of course a lot of human stuff like space station, of course Apollo missions before that, space shuttle, all those different things. What we do at JPL here in Pasadena, California is all the robotic stuff. So the missions to Mars, missions to Saturn, Jupiter, the Voyager spacecraft, which are in our, kind of flew by all the planets and are now slowly leaving are going to interstellar space. All of those spacecraft were built here in California and then launched most of the time out of Florida. Occasionally we just launched our most recent mission to Mars, also from California. So I don't know how many of you guys saw on Monday when we landed InSight on Mars. You can just do quick hands because I can see you guys, but I can't actually hear you guys, which is probably for the best. Yeah, I see a lot of hands going up. That's good. Awesome. So yeah, that's actually one of the missions that I got to work on a little bit in terms of because I worked on a previous Mars mission, I was able to help them review some of their stuff. But that's the kind of stuff we do a lot of. So now with that, let's go on a quick tour of the solar system. Here's a planet. I don't know, usually this is a guessing game as to which ones, but you guys can think in your head which planets those are. I'll give you a second. This one is Mercury. And think about this one. It's Jupiter. Here's another one, Saturn. This one, guys, this is a little harder one. This one's Neptune. That's our moon. Most people recognize that one. But this one is also our moon. So we sent a robotic spacecraft about a decade ago to the moon. It's in orbit, and it has taken pictures of the backside of the moon. So this is not a sight that most of us typically see because our moon is what we call tidally locked to Earth. So the same side of the moon always faces the Earth, but it has a very lovely backside as well, which of course a handful of people in history have been able to see, but now all of us can see thanks to some of the robotic spacecraft around the moon. This is also a moon. I don't know if you guys can guess which one. This is Jupiter's moon Io. It is the closest of the large moons to Jupiter. And what you're seeing, that yellow is sulfur, a very stinky, rotten egg kind of smelling moon. And each of the black spots that you can see there are volcanoes. So this is the most volcanically active moon, actually the most volcanically active place in the solar system. And that's because it orbits so close to Jupiter that the forces of gravity that Jupiter exerts on it create this sort of intense amount of heat, which leads to the volcanism. So lots of volcanoes, not particularly a great place for us to go. There's another moon. This is also of Jupiter. This one's called Europa, and it's the second of the large moons away from Jupiter. And this one has some really cool features, which I'll get into a little bit later. This, guys, is Phobos at Mars. It's a little wonky. It's a very small moon, relatively speaking. It actually orbits very close to the planet, so that if you were on Mars, you would see this go in the sky. It would kind of drift forward, and then a few hours later, you'd be able to see it again as it orbited the planet. It's actually so close to Mars that eventually, in about 10,000 years or so, it will get torn apart by the planet and fall into the planet. So it's a moon that has a kind of a relatively short lifetime. Here's another moon, and not a ravioli. This is Pan at Saturn. Very strange moon that got somehow flattened out in the middle, or two parts smashed together to create this. This one's not a moon, for those of you guys counting. But this is Mimas, also at Saturn. So it looks a lot like the Death Star, of course, which we love. That's Herschel crater, which is one of the largest craters in the solar system that we can see. Obviously, it largely affected the shape of this moon. And that's our planet, so a very special place, Earth, of course, and right now the only place that we know of in the solar system with life. So that's kind of why we're as scientists. If you're trying to understand how things work, you need more than one data point, right? So Earth being one great data point. Now we're looking for more data points to help kind of understand the context. And part of that's kind of a neat story, right? So if you think about physics or chemistry, the things you guys are learning, those are true basically everywhere in the universe. So if you were to travel to a planet, 100 million light years away or whatever, in a different galaxy, the laws of physics would basically be the same as you're used to here. You wouldn't really have to change your understanding of the world. Chemistry is the same way. You can react things in different places and they basically react the same way. But life, unfortunately, is like one of the big pieces of science that we don't know. So if you went to another planet, you have no clue necessarily that life looks like us, or kind of even looks like the other things on this planet. Even on Earth, we have a pretty wild variety of planets. And I'll show you guys some examples of that later, of like different types of life. So it's kind of it's a cool way of thinking about things and trying to understand whether life is universal, whether life looks like kind of similar to us universally. Those are some of the really interesting challenges that questions that we're trying to answer. So we'll begin with one of our neighbors, Mars. And so Mars for a very long time has kind of been, of course, fascinating to us. There's a bit of a history to that. So when we finally got telescopes good enough and Mars would come close enough, we got these pretty good drawings of Mars. This is one of the early drawings by Schiaparelli, an Italian astronomer who kind of sketched out these things. And he saw a lot of dark kind of striped features, which unfortunately in the English translation got translated to canals. So these are really channels, but the word canal, of course, and like in our language, means usually like somebody built it, right? Like if you think about like the Erie Canal, that's like humans built the Erie Canal. So then that spawned a bunch of science fiction where people were like, well, if someone's building canals on Mars, there must be Martians. And we got some early examples of sci-fi where Martians would come to Earth and things like that. In this case, imagine sort of those weird octopus-like creatures. So we were very fascinated always with the potential of life on Mars, and we sent a few spacecraft there. This is a Mariner 4 spacecraft. This is really the state of the art, of course, in the 1960s of quality. And you can kind of see, like, obviously by today's standards, these images aren't particularly great. But what you see in the picture is a bunch of craters that look pretty well intact and nothing that is kind of eroding them. So all the craters we see on Earth, for the most part, are eroded, damaged by life sort of taking over or water breaking it down. So we don't actually have a lot of examples of our history, but on Mars, you could see a very well preserved history. And the other neat thing this spacecraft did as it went by Mars is it actually looked through the atmosphere back at Earth, and we could tell how thick the atmosphere was. And it's about 1% of Earth's atmosphere. So, I mean, you guys, like, you can get an airplane, they tell you, like, of course, if something should happen, that you have to put your mask on to breathe oxygen. And that's at about 35,000 feet. The density, like the amount of atmosphere on Mars, is about what you would see at about 100 or 120,000 feet on Earth. So almost nothing to breathe there. And of course, on Mars' case, it's not so much oxygen as it is carbon dioxide. So it wasn't a particularly hospitable place for life, and we didn't really see a lot of evidence of water. But we were still kind of like, well, let's keep going back. And fortunately, on the next mission here, Mariner 9, now you can see a lot of evidence of water. So these are features that, of course, are dry now in these images, but you can see that something must have flowed on Mars once. So we knew that there must have been water on Mars. You see these kind of creek features and deltas. You can see walls of the craters have been breached where like liquid would have flowed into the crater. So now this is a world that looks a lot more alive. And of course, we were like, well, that's worth investigating. So we sent a pair of spacecraft in 1975, launching in 1970, arriving in 1976 on Mars, called Viking 1 and Viking 2. And these were the first robotic landers here from JPL that landed on the surface of Mars, and saw a very kind of dry world, desolate world. Rocky here, this is Viking 2, so a little rockier than Viking 1. What they did is they gather a little bit of dirt. They couldn't move, but they had these arms that would go out, and the arm would gather some dirt, and they would put it inside the robot, and they would do 3 different types of experiments on it and look for life. And it was really exciting. Of course, this is, the technology then was groundbreaking technology. And unfortunately, they had 2 instruments say there's no chance, nothing here looks like it's alive. And a third instrument was like, well, maybe we can't tell what's happening here, but in science, we can't jump to conclusions. So because it was not a real great answer, they said it's probably explainable by other things that are not life, because the first 2 instruments said it's not life. So it was then a long time before I went back to Mars, because we went really we went big, and then we're like, well, now we're going to go home. And we did a bunch of other stuff, of course. But then starting in the 1990s, we started sending more rovers. And here's one that I worked on called Curiosity that we launched in 2011 and got there in 2012. And with our series of rovers, we started looking for water on Mars, which we found a lot of evidence of. And with Curiosity, we started asking the question of, could Mars support life, or could it have supported life in the past? And incredibly, the answer within the first few months of landing on Mars was that the answer was yes. So we saw a lot of evidence where we landed would have had a lot of water. It was about a lake that probably was at waist high or higher. The water was pretty fresh. So we think we could even, it's possible that humans, if we had, had that water, we could drink that. And it had enough ingredients in it that certain types of life as we know it on Earth could have survived in that. So 3 to 4 billion years ago on Mars, you have a pretty warm, wet environment that could have been home to a lot of life. It certainly would have supported that life. Whether the life was there or not, it's still a question that we were trying to answer. And then what does it take, of course, for habitability? So you need the water, you need some sort of liquid for things to survive in, you need energy. That comes from warmth, it can come from chemical reactions. Sometimes it can come from nuclear material as it decays, it gives off heat. You need chemistry, so the ingredients for life: carbon, hydrogen, nitrogen, oxygen, potassium, sulfur, all those things that we're made up of. And time. You need time for all those things to interact with each other and eventually maybe form the beginnings of life. And so we go out in the solar system to Jupiter, and in particular, Galileo made these observations of these various moons around Jupiter, which we later called the Galilean moons. And this is in the 1600s. He marked these little stars that looked like they were going around Jupiter, and that's when he realized, of course, that things orbit other planets besides Earth, and not everything goes around the Earth. And that led to, of course, our understanding of the modern solar system. So the Galilean moons, of those, we saw Io earlier, and we saw Europa. And here's a kind of a nicer picture of Europa that you can see. This is taken by our Galileo spacecraft that was there basically in the 1990s all the way into 2003. So there's a couple of really neat things to sort of just enjoy about this picture. So one, you see these beautiful stripes across the surface. You see the orangish material, which we're not exactly sure what it's made up of. We believe it's some sort of salts that are reacting with the radiation. But you also will notice there's not a lot of craters. So when you look at the moon, for example, even from here, you can see a lot of craters. You look at Mars, there's a lot of craters. And that tells us typically the age of those places. So you know how you count like tree rings to tell how old a tree are? With planets and moons, we can sort of use cratering to tell us how old they are. So the more craters, the older the surface is. And areas where there are fewer craters means somehow the surface has evolved. So on the moon, you actually can tell that there's different ages because some of the areas have more craters, and other places have had some sort of lava flow where that's wiped out the original set of craters, but new craters have formed. Kind of a quick way of aging things. On Europa, you'll see like one right around the middle, but you don't actually see a lot of craters across the whole moon. This isn't just this picture. And that's because we think Europa has a very active surface. And the reason we think that is a couple of reasons, but we know that Europa is mostly made up of ice, but we think that ice is somehow breaking up and resurfacing so that these craters that would definitely have happened at some point have all been erased. And now we only see the evidence of pretty recent craters. So I'm going to go through this. It gets a little bit fun here. There's also these stripes that I showed you earlier. And one of the things we can see are the kind of like where the fault lines are occurring. So you can see here that there was a stripe that somehow got broken up by a new stripe that like sort of a crack that forms across it. So these ridges that are like forming over time are definitely evolving and then, you know, moving relative to each other. And the other thing that we used was Galileo carried basically a magnetometer on it, which is really similar to the the metal detectors that you guys maybe have used at airports or places like that. So the way that works is, like at an airport, is if this metal detector has basically a small magnetic field. As you walk through it, any metal on your body basically reacts to that magnetic field and creates a very small magnetic field of its own. And then a detector in the metal detector says, hey, there's a small magnetic field that I'm not responsible for. Therefore, there's metal on this person. We actually did the same thing at Europa. So Jupiter has a pretty strong magnetic field. And as we flew past Europa, we could see that Europa was reacting to Jupiter's magnetic field. And that reaction implied that there was a lot of liquid water. So that the surface that we knew was ice was probably pretty fluid underneath the surface. And with a little refinement of that data and kind of models that we have, what we thought about Europa was that it has this ocean core. I'm going to click play here. Hopefully this animates reasonably well for you guys. So as Europa orbits Jupiter, it kind of gets squished and expands. And that's because it doesn't orbit in a perfect circle. So sometimes it's closer to Jupiter and sometimes it's farther from Jupiter. So as it gets closer, it gets squished a little bit, and it gets farther, the backside stretches out a little bit. And so you see this sort of heating. What happens is like the friction kind of goes in there and warms it up, and that warms up the ice and creates this ocean layer. So we think Europa actually has an ocean layer that is the entire moon. And based on kind of the estimates that we have, we actually think Europa has 2 to 3 times the water of Earth. So you're talking about a moon about the same size as our moon, with 2 to 3 times the water and an ocean that is global. As you can also see here a little bit in this image, you'll see that the water interacts with a sort of a rocky core. So you also have the ingredients that we talked about earlier, the chemistry for things, and you have that warmth from the friction caused by this heating, right? So if you rub things, they warm up. The same thing is basically as the interior of Europa rubs against itself, it warms up. and that's warming up that water. So you have the energy, you have the chemistry, you have the water, and we think this has happened for billions of years. So you also have the time, which means for us, Europa is one of the best candidates for habitability and maybe even life in the solar system. So we're working on a mission there called the Europa Clipper Mission. And this mission will basically orbit Jupiter, but kind of fly by Europa every so often, about roughly every 2 weeks. And we'll do a bunch of data analysis during that time to look at what the composition of the surface of Europa are, as well as what we'll do is we have an ice penetrating radar. I think I have that. No, I'll get that in a little bit. We have an ice penetrating radar that can kind of help us determine where the ocean and ice interface is. So we can tell how deep the ice is and how deep the ocean is. We can also, as we're flying through, we'll start looking for evidence of things that are in the kind of, we're going to call it not the atmosphere, but in orbit around Europa. The reason we're doing that is Hubble images of this, and the Hubble image, this black and white is not the Hubble image. The blue and white here that you see is the Hubble image. And this area down here, where my mouse is, I don't know if that shows up, hopefully it does, but in the lower left is kind of a little wider than the rest of the areas, and that's because we think there's plumes there. So we think there's some sort of water ice or liquid water that's shooting out of Europa in that southern hemisphere. And that would be basically a free way for us to fly by that and get some sample of what the interior of Europa is like. So we have instruments to look at that as well. And an example of that actually we know already exists in the solar system. At Saturn's moon Enceladus, there are these geysers like this, also in the southern hemisphere. And the Cassini mission flew by them and found, of course, evidence of liquid water as well as a lot of ingredients to support life. So we're hoping for the same thing at Europa. And that's actually one of many worlds, it turns out, that have these kind of oceans in them, what we're calling ocean worlds. So, of course, all the moons of Jupiter have it. Many of the moons of Saturn, places like Pluto have water as well. And then some just kind of course, our planet Earth has a fair amount of water. But one of the neat things about this sort of finding in this kind of research area is we used to think that it was only planets that were near their star in the right distance, like the Earth is from our sun, to have liquid water were the only places to look for life. And it turns out there's all these moons and other places that you can also look for life. This is, I think, one of the coolest things. In the last 20 years or so, we've kind of, I got to click play on this one, I think. Does this play? Maybe. No. Cool. All right. Well, you're going to have to use your imagination. Unfortunately, I can't figure out how to make this play. But this picture is a picture of our Milky Way. And right around the center of this picture, we had a mission looking at all these stars called Kepler. And the Kepler mission stared at the stars for hours at a time. It was about 6.5 hours at a time, and would look for any dip in the brightness of the star and would wait basically patiently. We would do this multiple times at the same section. And what they found were those dips in the brightness of the star are when a planet passes in front of it. So every time a planet passes in front of the star gets a little bit dimmer. And what we found were about 4,000 or so planets around stars, which we didn't even know of about 25 years ago. And of those, about 12 or so planets fit into the right distance around their star to support liquid water. They're rocky planets, kind of like Earth. They vary a little bit in size, from a little bit smaller to us to mostly larger than us, but all the right distance from their star to have liquid water. And of course, we saw a lot of large planets like Jupiters and Saturns that are really big. And all those we expect would probably have moons. So the places for life to arise are not just here on Earth, or not even just in our solar system, but really all over the cosmos. So we think the odds are pretty good for that. And last, I'd like to kind of end on this little picture here. This is a picture that Curiosity took. It's one of my favorite pictures Curiosity took. What you're seeing at the bottom there is Gale Crater, which are the crater that we kind of landed in the middle of. And if you kind of look very carefully, you can see a small speck in the sky, and that is the planet Earth. And so that's basically everybody, all the life that we understand is one little pixel in the night sky of Mars. And Curiosity took that picture. So I'm very hopeful, of course, one day that we'll find another little speck that has life on it. But in the meantime, we're trying to explore to help understand that story. So with that, I'm going to turn it over to the Q&A part of this. I'll turn back to me.
Yeah, as you turn it back, that was outstanding. What a great picture from Curiosity. All right, guys. So yeah, we'll start with Miss Searson's class. If you guys have a question, Oh.
Yes, we do. Yes, sorry. Gracie, go ahead.
How long would it take to get to Jupiter?
Can you guys see me?
Can you guys see me?
Yeah.
Okay.
Yeah. The question was, how long would it take to get to Jupiter?
Yeah. So with the Clipper mission, there's two different ways of getting there. One is with the rockets we have that are flying today. It takes about 7 years to get there. And the reason is because you have to get a lot of energy. So you can think about it, right? The Earth is kept in orbit around the sun because the sun has so much gravity. If you want to get farther from the sun, you need a lot of energy to get out there because you're basically trying to escape essentially the sun's gravity. Of course, and then if you're heavier, you need more energy to do that. So current rockets are pretty big, but not quite big enough. And so what you end up doing is you fly past Venus and Earth a few times. And every time you fly past them, you get a little bit more energy, what we call a gravity assist, or some people like to call it a gravity slingshot. And so you get enough energy eventually that you can fly out to Jupiter. The other thing is NASA's working on what we call a Space Launch System, which is an even larger rocket. And that rocket would have enough energy to launch you directly to Jupiter. And that would take you about 2.5 years. So right now, if you go directly to Jupiter, even if we have larger rockets, it'll still take 2.5 years.
Very cool. All right, let's go to Miss Curtin's group. You guys have a question?
Yeah, go ahead. Just stand nice and close. So, I've heard the giant red spot on Jupiter is a storm, like a tornado. But I'm used to hearing that tornadoes have to touch down on a solid surface. But I've heard Jupiter is completely gas. How would that end up working?
Yeah, great question. So we actually have a mission there called Juno right now, which is trying to help understand the composition of Jupiter, whether it has maybe a small core in the middle. In Jupiter's case, with the Great Red Spot, we've seen that spot continuously for over, I think, 180 years. We think we may have also seen it in history, like people have written down about a large storm on Jupiter. We're just not sure it's exactly the Great Red Spot. One of the things about that storm is also it's dying. So it's slowly getting smaller. It's gotten smaller in the last 20 or 30 years, even since we started like looking at it with spacecraft that have flown by it. So we know eventually it'll die out. Jupiter's atmosphere is pretty wild, and there's a lot of stuff happening. But what's happening in general is you have a lot of areas. There are bands of winds, but you have a lot of areas where hot gases are rising and cold gases are sinking. And so that creates that sort of turbulence, and that creates that sort of spiral effect that you see in hurricanes. The same thing is happening in hurricanes. So hurricanes, of course, pick up a lot of their energy coming over water and then kind of release it over land. In Jupiter's case, we don't necessarily think there's an overland part. A lot of that is just slow dissipation as the area passes over, evens out. So it doesn't necessarily get as hot or necessarily as cold. So we're still kind of understanding the atmospheric dynamics of Jupiter. So we'll have a better answer to that question in a few years. But the theories that we think are causing these storms are essentially these turbulence as kind of bubbles of hot gases start rising and other sort of pockets of cold air start sinking down.
Very cool. Before we go to our third class, I just want to note we have some groups watching on YouTube Live. If you guys want to pass on questions in the chat bar, I will pass them directly on. So please do that. But for now, let's go to Miss Russell's class. If you guys have a question, come on up. And
I do.
Sedgman.
What sort of life do you think is on Jupiter?
So I think Jupiter probably doesn't have life. It's a pretty harsh place in terms of we don't really know if there's a solid surface to stand on. And even as you go below the atmosphere, the pressure is strong enough to crush like things like us. But like I said, they think the moons of Jupiter are pretty good candidates. Particularly, we think Europa is an awesome candidate. Most likely, the answer, if there's life there, is it's something kind of like microbial life. the small kind of single-celled, maybe small multi-celled organisms. If you're a little bit of a dreamer, like I think a lot of us are, we'd like to see whales and fish underneath the surface. It's probably not likely to end up in the same way, but there's always a chance.
Awesome. All right, let's take one from Miss Ing's class. You guys have.
All right. Do you think that we'll ever have to colonize on other planets? And if we do, how exactly would we do that?
I'd like to believe we don't have to, just because this is a pretty solid planet. Even if we try to kind of live on other planets like Mars, which I think most people are thinking of, it's going to be really rough. The first multiple generations are basically just going to be struggling to survive. Whether you survive the trip from Earth to Mars anyway, which is tough enough. So it'll always kind of be like a very stressful life, comparatively speaking, to Earth. So I don't think most people are going to want to try to leave. Eventually, when our sun dies, we'll have to leave, because it'll expand and consume the Earth in fire. If you get past that point, or you get near that point, I think what we'll probably end up with is what we call generational starships. So ships that would travel, that would basically be small worlds in their own, and people would live in them and live for multiple generations as they traveled from here to a better star system.
So just as a quick follow-up, when is the sun scheduled to burn us all up in fire?
Oh gosh, I'm so bad at this. I want to say it's like 500 million years from now, so it's not. Don't worry, no one has to lose any sleep tonight.
No, don't cancel your insurance. All right, let's go to Mrs. Karakaisis' class. Do you guys have a question? Come on up.
What?
Yeah, you. Yeah. I know. It's exciting.
Oh my gosh. Do it.
So my question is, if there is any life on any of the planets, even the moon, Mars, any of them, have you seen any signs so far?
So the answer is no, not really. One of the things that's actually really tough is there's a lot of evidence, even in your classroom right now, of life that you wouldn't necessarily recognize as evidence of life. I mean, besides you guys. So the plastic chairs you're sitting on are evidence of life, because the petroleum that plastic came from is formed from organic material that was trapped for a long time and became oils and petroleum, things like that, right? So like a lot of oil and gas in your cars is dead dinosaurs. So it's actually really tough for us to always notice that there's life or evidence of life, and that's one of the big problems, right? Because you don't think of a desk or a chair as evidence of life, but it can be. So that's one of the things we're still trying to understand. And so the story that we're working on at NASA is, let's figure out first, is there water? Was there an environment, or is there an environment that life could survive in? And then based on that knowledge, what do we think the life could look like? So we're actually sending a mission in 2020 to Mars that will look more directly for evidence of life. So we'll see if that one detects anything like ancient life or even present life on Mars.
Very cool. All right, let's head to Ms. Goff's class.
How do you get the job you have?
Okay, so I got the job I have. Couple of reasons. One, I really wanted this job, and so I kept applying. But two, I was very lucky. A classmate of mine in college got hired here at NASA, particularly at JPL where I work, a couple years before I did, and we were good friends. And so when he got hired here, I mentioned that I applied. And so he helped contact more directly people who were looking for kind of people to work here. So that was 15 years ago, and it's been awesome ever since. But that's one of always it's a good advice is inevitably, as you meet people, some of them are going to have really cool jobs in their life. So it's really important to kind of maintain those friendships and connections, so that if they do have those cool jobs, and then you want one of those cool jobs, it's a lot easier to find them than just trying to apply hundreds of other people.
Yeah. Excellent. And then we'll wrap up our first round of questions with Mr. Windish's class. You guys have a question?
Right there.
Did you always wanted to be an engineer?
No, I started out as a physics major. Generally, I think I like understanding how things work. So just kind of like curious about the world, and physics seemed like it had a lot of the answers. But one of the nice things about going to college was I got to do a lot more physics, and I worked in a physics lab. And I realized that the thing I also like doing was building things. So you can do both. There are people who are who work in physics who build a lot of stuff. But it turns out that engineering was kind of a little bit better for me. So it's sort of taking the physics knowledge and then applying it to building things, which gives you a really good understanding of how things work. And what I work on now is actually how things break. So I think about all the different ways spacecraft can break, and that really gives me an amazing understanding of actually how they work. So just think about it, like, right, if you ever had to repair something or fix something, you learn a lot more about how it works than if it's just working fine.
So if like the remote control breaks at your house, you can just like rip that out, right?
I have repaired my TV at home actually when it died. I took it apart and resoldered some parts on. So I can actually say that some of my engineering is useful.
Nice. All right. Do you have time for another round of questions, all 7?
Yeah, of course. Let's do it.
Let's go start with Miss Searson.
Someone wanted to know if you believed in aliens.
So the short answer is yes. I think just given like, kind of what I talked to you guys about, right? So one, there are places in our own solar system besides us, besides Earth, rather, that could be places for life to arise. And then if we look at the data from other stars, we see so many planets. We think the vast majority of stars that you see in the sky have planets, and probably multiple planets. So it seems like if you add up the billions and billions and all the different cases, it seems pretty likely that life will show up on one of them. Now, the big problem, of course, is that the universe is giant. And so it's very hard to get from place to place. So it's not always, it's not clear to me that aliens would come visit us or anything like that. But do I believe that they're alive out there somewhere? Yeah, I kind of have to have hope. But I'm still pretty optimistic we might find something in our own solar system. Even if it's one of the questions that you might try to ask is, like, if Mars 4 billion years ago was such a good place for life, isn't there a small chance that life could have started there and then come to Earth on an asteroid, so that we might all be the Martians here? So we might be the aliens on Earth. So it's food for thought.
Very cool. I do want to contrast something there, which is interesting. So you talk about life in our own solar system, and I think when a lot of people mention aliens, they mean intelligent things, bipedal things. They think of sci-fi.
Yeah.
So have we definitively concluded that there are none of those in our solar system?
I mean, there's a chance, certainly, of that, but pretty unlikely, right? I mean, so yeah, some of the candidates at this point, if you were looking for that, would have to be subsurface, right? We would have seen evidence of surface dwelling, I think, intelligent life in our own solar system already. But subsurface dwelling, it's always a possibility. It's, yeah, like I said, maybe there's whales underneath the oceans, in the oceans of Europa. Can't rule it out yet.
Okay. Excellent. Let's head to Miss Curtin's group. If you guys have a second question.
Yes, theirs is a two-part related question.
Okay, good.
How do you get drones onto different planets?
Like, how do you get them to land? And
will any of the planets hit Earth in about a few years?
Yeah. Okay. Two questions. All right. So, getting things to other planets, it's pretty complex, and it's really fun. As again, excuse me, as those of you guys who watched us land something on Mars on Monday. Still very weird to be able to say that. So right, there are a couple things you need to do. One, you need to essentially build the thing that's got to land somewhere. Then you got to send it out from Earth on a giant rocket. So it has to basically kind of leave Earth's gravity to get to the next place. When you get there, you're often going too fast, right? Because like when InSight kind of got to the top of the atmosphere at Mars, it was going about 12,000 miles an hour. So you would crash in. So you need to find out different ways of slowing down. So if you have an atmosphere like Mars or Earth do, there's a couple of great ways, which is that you can basically create friction with the atmosphere. So you like if you've seen like the capsules or shuttle, everything, right? They would basically get the broad side of them into the atmosphere, so they're kind of slowing down a lot by rubbing against the atmosphere. On Earth's case, you can actually do that pretty close to the ground. You can get pretty slow that way, and then you can open up a parachute. In Mars, the atmosphere is not as thick, so you can get part of the way down, and you'll still be going like 1,000 miles an hour, which is obviously for no one wants to land at 1,000 miles an hour. So then we do open a parachute, but on Mars, that parachute is designed for traveling faster than the speed of sound. So on Earth, you can slow down below the speed of sound. On Mars, you can't. So we open a large parachute. That parachute slows us down to relatively low speeds, a couple hundred miles an hour. And then you need to use rockets to get the rest of the way to the surface. So with InSight, the rockets were on the bottom. With Curiosity, when we landed, the rockets were above the rover, and we lowered the rover on a cable to the ground. But those rocket engines are pretty small compared to what you need to leave Earth, because they don't have to get off the planet. They just need to slow you down quite a bit. And then you use them to sort of softly land on the surface. And then if you have like a drone, so the next rover, Mars 2020, is actually carrying a small helicopter with it. So that helicopter will deploy from the rover, and then the rover will drive away from it, and then the helicopter will fly off. We're also looking at a proposed mission to Saturn's moon Titan. Titan has actually got a really thick atmosphere, so much that if you basically strapped on large like wings, you could really fly on Titan, which is cool. So they're looking at sort of more like a traditional drone that would fly around Titan and do science. So we'll see if that gets chosen and built to go there. But that's because it has a nice thick atmosphere. You can slow down pretty easily in getting there. You don't need the rockets at the end. The last mission that went to Titan actually landed just on a parachute. So pretty cool. As for things hitting Earth, there will be asteroids and small things always. One of the things that NASA is tasked with is trying to figure out where all of them are and track their orbits and figure out how likely they are to impact Earth. Most of them will be pretty small. Many of them will burn up in the atmosphere. A few of them will make it as small rocks down to the surface. But every once in a while, there can be some large ones. We're not worried about planets. The planets and moons are all pretty safe. But the larger asteroids could still be problematic. They can cause a lot of damage. So we're trying to track them. And then, of course, if we did find one that had an orbit that would eventually intersect Earth, we would try to figure out how we could adjust the orbit of it. So we probably would do that with a very small spacecraft that just kind of tugs on it a little bit. So it wouldn't be like Armageddon. It'll probably be more like a little satellite that goes out there, like locks onto it, and then just sort of burns an engine to change the orbit so that it never, or very low likely to come back to Earth.
Very cool. You mentioned at the beginning that InSight and recently landing on Mars. I urge all the classes when you're done to look up like YouTube videos of the control room for InSight. Because like you want to see a bunch of passionate people that spend a decade of their life working on the mission and how excited they are when it all succeeds. It's really cool stuff.
It is.
Cool. Let's head to Miss Russell's class. If you guys have a second question, just come on up.
When you get a chance, will you tell us again what that's called so we can look it up?
And whoa! There you go.
Hello. Hi. So my question is, do you yourself understand the event horizon of a black hole, and could you explain it to us?
Oh gosh, no. I mean, I understand like the most basic things of it, which is so fundamentally gravity acts on light. So there's a function of this, right, where you think of we can actually do this. And so one of the weird things about the universe is we see what we call gravity lenses, which are these little areas of very strong gravity that bend the light around them. And in fact, that creates almost like a telescope, because a telescope, right, the glass is bending light so that it hits your eyes. Gravity in that case is also bending light so that these objects that are behind the large source of gravity are bent around it and then come to hit Earth. So sometimes you'll see like a galaxy that's beyond this large gravity field, and you can see the galaxy get split up as it like the image looks like it's split up, but we know it's one galaxy. So a black hole is kind of similar to that. So the gravity of a black hole is so tremendous that the light in this case is bent all the way into the black hole. And because light effectively is how we perceive the universe, everything is perceived at essentially the speed of light. what happens there is, or that's really how information, I guess you could say, information is transmitted. So like all the radio waves, all the, the things that you kind of like, not even, well, computers are electrons, but all that information is being transmitted at the speed of light, and the way you receive in your eye and the way your computer receives it on the Wi-Fi. What happens at a black hole is, because all that that information is now being bent all the way into the black hole, effectively, it's as if that information, once it goes beyond that closeness of gravity, is all pulled in there. So then it's its own context. So everything for us on the outside appears like nothing can emanate from there, because everything is always being bent back in. And then there's the weird things like, once you're there, do you get spaghettified and all these other weird things that I don't truly understand. But yeah, the simplest explanation is basically that the gravity is so strong that no information, we think, is really allowed to leave that space. So you just can't see anything, or you can't transmit any information or anything like that.
That's a very good explanation, and just so that was good.
Yeah.
About 2 days ago, we did one with it was a black hole physicist. So if you want to see the full,
do that.
20 minutes.
So cool. It's so cool.
All right, we got time for 4 more quick questions, guys. So let's start with this Ings class. If you guys want to come up, go right ahead.
Sure.
Hey, take your time. Don't hurry.
How many years does it take to get into your field of work? And if so, what makes you choose that, and what are the main things you do in it?
I got pretty lucky. So, I mean, I went to college, and then I got my master's, and then I went straight to working here. In terms of like finding like my place here, it took a little longer, I think. I mean, I like the work here always, but I really found, I would say, my own groove about maybe 4 or 5 years into my career, like where I realized what I wanted to actually do in kind of in the bigger context of engineering and space engineering. So yeah, it's not trivial. I think the main thing I always think about, like for stuff like this, where we're talking about how it could take a decade or so of your life to get to Mars or do things like that. Is finding little stuff along the way that makes you excited about it. Little tests. It's really cool, honestly, even if it's not the final thing, to have a small piece of your design start working, even if it's on Earth, and then to kind of keep remembering that the bigger picture is like thousands of these things working, and then going to Mars or wherever you go. But it's tough, honestly. Like there's no easy answer. It's a kind of like you just got to set small goals along the way that feel like victories when you meet them.
Excellent. That's a great answer. Let's go to Mrs. Karakaitis' class. If you guys have a second question. That's you. I know. You're like perpetually excited that you guys get to be part of this. That's why we do it.
My question is, how does a black hole form, and have you ever seen a black hole in the things?
Oh man, I'm really not a black hole expert. I wish I should. I feel like everybody loves black hole questions. I believe it's a collapsed star eventually. Typically it starts with a star that was very heavy, or a large star that eventually, as it when it gives up, essentially when it dies at the end, because there's not enough material to react. Yeah, what's left is basically pulled into each other by its own gravity, and then effectively keeps getting collapsed smaller and smaller until it creates this sort of black hole. But yeah, you're explaining. Oh, you explain it. You're sitting here.
No, that's good. No, so it's a huge star. It dies. It blows up in a supernova, and what's left gets sucked in and makes a really, really dense star that sucks in all the light, like you said earlier. So
yeah. Thank you.
Cool. Let's go for our last two. So Miss Goff's class, you want to start?
We have Maddie.
Uh-oh.
There you go.
Okay.
Hi.
Nice planet. Why do you think planets have moons?
Why do I think planets have moons? Well, so most of the moons, well, I shouldn't say most. Many of the moons we think are formed around the same time as the planets. So, right where the kind of balls of material, right? So like you think of generally like you got a big solar system and it's full of, at the start, it's just full of a lot of dusty, material, and that stuff starts colliding and forming bigger and bigger balls of stuff, and you get things like our asteroids and planets, and eventually you also get things that are like not quite planets. And so a lot of these are basically what you think of them like a swirling, group of material. So what happens oftentimes is the center of that swirling group of material forms a planet, and then some of the outside stuff starts bumping into each other and forms its own little small ball of material. And if the way the swirling, right, the physics of the swirling kind of works out, is that stuff keeps swirling around, but now it's just a ball of stuff. So oftentimes you end up with a moon where you end up with a lot of the same ingredients as the nearby planet, but it's there. Occasionally, we think there might be evidence of things getting captured, like asteroids or things that as they're passing by a planet, they get captured. There was some thought that Phobos and Deimos, which are the two moons of Mars, might be captured asteroids. I don't know if that's actually been proven. So they just might have passed by Mars enough. And then there's weird ones, I think, like our moon, where there's still a hypothesis that a very large object hit Earth, kicked up a bunch of material into orbit around what was left of Earth, and that reformed eventually into our moon, which is, I think, one of the leading theories for how the moon got formed. So we're similar to the moon, but not quite entirely the same as the moon, which sort of implies that something big happened. And we see a little bit of that on Mars, actually. You don't see the moon part of it, but you can see these large events, because if you look at a globe of Mars ever, you can go online, you can see the northern hemisphere is very flat compared to the southern hemisphere. So we know something very large hit Mars at some point and kind of resurfaced the north, while the south stayed intact. So there are evidence for these kind of large impacts over history that could cause, moon-like things to form. So it's definitely, within the realm of possibility.
Super cool. And for the classes too, if you ever want to look up the science or space art of how our moon formed, it's really cool.
Yeah.
There's a huge collision. I mean, when two planets collide, that leads to some good pictures. Let's take a last question for Mr. Windish's class, and we'll wrap it up with that.
How many times did you go through the engineering process with Curiosity?
Good question. All right, so so the engineering process, like big picture, obviously, we really only went through it once, where we designed something, we started figuring out the details of that design, we started building it, and then testing it, and eventually building the unit that would go to space. But within each of those periods, you end up doing a lot. So Curiosity, at one point when we came up with the design, had two big arms on it, and had a weird shaped mast, and we have one nuclear power unit on the back, had two nuclear power units on the back. So you sort of evolve the design, and then some various reasons, someone's like, you can't do it that way. It might be it's too heavy to land on Mars. It might be, oh, it's too expensive to build that way, or it's too complex. And so you kind of go back and reevaluate the design. And then in your test program, as you start building it out and you're learning from it, you start also realizing that you have to change things. So sometimes you go back a little bit. And so I if you think about it that way, you obviously do these a lot of times. But big picture for missions like this, we tend to really go through it one big time. Where that being said, for the next rover, Mars 2020, it looks a lot like Curiosity because they're using a lot of this stuff. So they still went through the process one time, but it's basically think about it as a Curiosity 2.0 at some level. So it's more like software where you build one version, and then once you do that, you can kind of evolve it into a version 2.0. So the next rover is a little bit more of an evolved rover.
Outstanding. Bobak, so you might want to turn down your volume, because at the end of every hangout, what we do is I'm going to demute everyone's microphone. So boys and girls, your class, if you could join me in saying a big thank you and goodbye to Bobak for joining us today. So guys, go right ahead. Thank you so much. Thank you so much.
Yeah.
I think you're inspired for people in space.
Awesome. I love it.
Awesome.
Thanks, guys. Thanks, guys.
To our classes, yeah, thanks so much. Great questions. We hope you join us again soon, Bobak. That was great, and look forward to having you back whenever you can.